We started this section 5.1 last time on the area and distance problems, and this is our introduction to integral calculus. So last time we presented the area problem, which was basically a strategy for how to find the area below a curve down to the x-axis over a given x interval. And we developed our strategy, and we saw that the concept of a limit needed to be used in that strategy. Now we're going to move to the distance problem, and it's a seemingly different type of problem, but we'll see how closely related it is to the area problem as we formulate our strategy for the distance problem. First, we'll describe what we mean by the distance problem. So the idea is, if you know the velocity and the time traveled, can you find the total distance traveled during that time? Now, if the velocity is constant, that's a very easy problem, right? We're all familiar with the formula distance equals rate times time. But what if the velocity is not constant, right? And that's common. If you're driving your car, you usually don't stay at the same velocity the entire trip. So this formula isn't going to work straightforwardly in the case where the velocity is not constant. And that's the problem we're facing in the distance problem. We want to develop a strategy for finding the total distance traveled in the situation where the velocity is not constant. So let's look at this example. Suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds, and they're recorded in this table. So the velocity in miles per hour is recorded every 5 seconds, and notice the velocity is not constant, it's changing, for a total of 30 seconds. So we've got our velocity information, not at every instant, but every 5 seconds. Now just to make the problem into the units we want to use, we're going to convert from miles per hour to feet per second. And so we use this conversion factor, and so we now have all of our velocities in feet per second. So let's look at the first 5 seconds and see if we can figure out how much distance is covered during the first 5-second interval. So notice the velocity starts at 25 feet per second, and by the time we get to the end of the 5 seconds, it's increased to 31 feet per second. So most likely it gradually increased during that time, although it could have gone up and back down, we don't know. But it changed over that interval. But it didn't change a huge amount, right? There's not a huge difference between 25 feet per second and 31 feet per second. So what we're going to do is assume that the velocity stayed constant during that 5-second interval. By assuming it's constant, we can use our formula distance equals velocity times time. Now, what constant are we going to use, right? We could use 25, we could use 31, or we could use any number in between. All of those would be reasonable estimates for assuming the velocity stayed constant during that time. But we're going to choose right now to use the starting velocity and just assume it stays at that velocity the entire 5 seconds. So that's our assumption here. So then we just use our formula that we saw on the last slide, distance equals velocity times time. And since we've assumed velocity is constant, we can now use that formula. So we plug in 25 feet per second for the velocity, 5 seconds for the time. Notice the units work out perfectly, the seconds cancel. 25 times 5 is 125, and then because the seconds cancel, all that's left for the units are feet. So the 125 feet, this is the distance traveled during the first 5 seconds. And so what we could do next is move to time 5 to 10 seconds, and then estimate the distance traveled during that time interval using a similar method, and work our way all the way down the table, estimating how much distance was covered over each time interval, and then we can add them all up. So that's kind of where we're going next. So following in that same pattern, we've already estimated the distance covered during the first 5 seconds. So now we move to the second time interval from time 5 to 10 seconds and use a similar approach. So we're going to assume the velocity stays constant over that time range. In reality, the velocity changed from 31 to 35 feet per second, and we're going to just take the starting velocity of 31 feet per second and assume it stays at 31 the whole 5 seconds. So again, we can use the same formula. Distance equals velocity times time. Plug in the 31 feet per second for velocity, 5 seconds for time. That comes out to 155 feet. So that is the distance traveled during the second interval, which is time 5 to 10 seconds. Okay, so then we just keep going over all the time intervals in 5-second blocks, and we calculate all these distances traveled. So remember this one here, this is the distance traveled during the first 5 seconds, time 0 to 5. And that came from assuming the 25 for the constant velocity for 5 seconds. This is the one we just calculated from up here, distance traveled from time 5 to 10. And then here from time 10 to 15, which is here on the table, we take the starting velocity 35, assume it stayed constant over 5 seconds, so 35 times 5 is the distance. We go all the way down to the last interval from time 25 to 30. We assume the velocity is 45 the whole time, multiply it by 5 seconds. And then when you simplify this calculation, you get 1,130 feet. So that's our estimate for the total distance traveled over the entire 30-second interval. Now we know it's only an estimate because we made that assumption that over each 5 seconds that the velocity stayed constant, and we know that's not really the case. Notice the velocity is constantly getting bigger. It never goes, well, no, down here it goes down. So our first approximation is an underestimate because we assumed the velocity stayed at 25 when actually it gradually got larger. And some of them are overestimates. Right here, 20 to 25, we assumed the velocity stayed at 47, but it actually got smaller, gradually smaller over that time interval. The calculation we just did, we made a certain assumption about the velocity staying constant, and we used the velocity value at the beginning of each time interval and assumed it stayed constant over the 5 seconds. So for example, on the first time interval from time 0 to 5, we took the beginning velocity of 25 and assumed it stayed 25 over the 5 seconds. We could have chosen that differently, right? One other option is to choose the ending velocity and assume that it stayed, in this case, at 31 for the velocity over the first 5 seconds. So if we did that, for our first time interval, 0 to 5, we would have a velocity of 31 feet per second times 5 seconds. And then plus, we add the distance traveled during the next time interval, which is time 5 to 10. Take the ending velocity of 35, multiply it by the amount of time, which again is 5 seconds, and we get this one. So using the ending velocity values, go all the way down through all the intervals, and we get 1,210 feet for the total distance traveled. So we got a different approximation using this method. But now we're going to go back to the first version, which is from the previous slide, which I copied here. So this version here is using initial velocities. So this is using the beginning velocity at each time interval. Okay, so that's back to the calculation we did previously. So now we're going to represent this graphically. So if you look at the graph to the right, the first thing we did was we plotted the data in this table. So we have a time axis and a velocity axis. At time 0, the velocity is 25, so we plot the point 0, 25. And then we plot the point 5, 31, and continue plotting all the data. Then we just connect those points with a curve. So the blue curve represents the velocity function. Now notice these rectangles. Now that comes from this calculation. It's related to this. Remember, over the first time interval, 0 to 5, we took the beginning velocity of 25 and we assumed it stayed at 25 the whole time. So here's the 25, and over the first 5 seconds we just assume it stays 25, so we keep the height 25 for the velocity over that 5 seconds. And then this calculation here, 25 times 5, tells us the distance traveled during the first 5 seconds. But the 25 times 5 could be interpreted as the area of this rectangle, because it has height 25, width 5. So I'm just going to make a note that area is 25 times 5. If we go to the second term in our sum, 31 times 5. This blue dot is the 31 from the table. So the height here is 31, and that from 5 to 10, that is 5 distance. So the area of this rectangle would be 31 times 5. And so the area, which is this term here, and that's the distance traveled during the time interval 5 to 10 seconds. So each of these areas represents distance traveled over the corresponding time interval. Okay, so we're starting to make this graphical connection that these rectangles are very similar. This whole setup here is how we approximated the area below this curve. So this is leading to the idea that if you have the velocity curve, the area below that curve represents the total distance traveled. This slide summarizes some of the ideas I was just presenting on the previous slide. So we had this calculation for our estimate for the total distance traveled, and we related it to this graph where each one of these products represents the area of one of these rectangles. And we also interpreted each one of these products as representing the distance traveled over one of the 5-second time intervals. Okay, so for example, the first rectangle, 25 times 5, is the area of this rectangle. That comes to 125, and that would be in feet. And that's our estimate for the distance traveled during the first 5 seconds. And then similar for all the other rectangles, they're all representing distance traveled over the corresponding time interval. And then when you add up all of these areas, we got 1,130 feet, and that was our initial estimate for the total distance traveled. In this example, if you remember from the given information, we only took velocity readings every 5 seconds. So we lost some of the information about the velocity. We don't know, for example, the velocity at time 1 second, or 3 seconds, or 4 seconds, etc. And without that information, we can't get 100% accuracy. We can only estimate the distance traveled. So if we wanted to make our estimate more accurate, we should take velocity readings more often. So here's a picture that shows that. So here, notice by the time we get to 10 seconds, we've taken 1, 2, 3, 4 readings. Whereas in the original, we were taking a reading every 5 seconds, so we would only have taken 2 readings over the first 10 seconds. So we're taking readings twice as often. And so we're getting velocity estimates more often. And then we use the same setup with the rectangles. We know each one of these rectangles' area represents the total distance traveled over this corresponding time interval on the t-axis. And so the plotted data also includes, right, these more points, that more measurements were taken during the 30 seconds. But you can see, just like how similar this is to the area problem, and the same idea, the more readings you take, that corresponds to a larger number of rectangles, the area is going to become closer to the area below the curve. There's going to be less gap and overhang of the rectangles compared to the curve. So the more rectangles you take, in other words, the more often you read the velocity, your estimate for the total distance traveled gets closer and closer to just being the area below the velocity curve. So this discussion helps to confirm what we suspected earlier, that if you have a velocity curve, the area below that curve over a given time interval, that area represents the total distance traveled over the corresponding time. We can now generalize what we saw in this last example. If you have some function that gives you the velocity at any time, we'll call that f of t, over some time interval from a to b. And to keep things simple, we'll assume the velocity is always positive, so it's always moving in the positive direction. It never moves backwards. So just like we did in the example, suppose we take velocity readings periodically, and we'll label here the times where we take the readings, t0, t1, t2, all the way up to tn. And then we assume the velocity is constant over each of those subintervals. We'll also assume that the spacing between these time intervals is always the same. So then we can calculate the length of each time interval using this formula. Take the total time interval, which is the ending time minus the beginning time, and divide it into n equal pieces. So dividing by n, since there are n subintervals here. And this gives us the time length of each interval. So we call that delta t, similar to the delta x we used earlier to represent the length of a small subinterval on the x-axis. Here it's a length of a t interval on the t-axis. So just like we did before, for the first time interval, we assume the velocity stays constant, and we use the beginning velocity as our constant. So since the beginning time interval is at time t0, the velocity at time t0 is found by taking t0 and plugging it into the velocity function f of t. Right, so this is the velocity at time t0. And so we take that number as our constant velocity, multiply it by the length of time of the time interval, which we're calling delta t, and this expression would be the distance traveled during that first time interval from time t0 to t1. Then we move to the second time interval from time t1 to t2, and we take the beginning time, t1, plug it into our velocity function, and assume the velocity stays at that constant for the entire time interval. So we multiply the velocity times the length of the time interval, and that product gives us the total distance traveled during the second subinterval. And so here, this was our estimate for the distance traveled during the first time interval, and then we add to that the distance traveled during the second time interval. Keep going through all the intervals till you get to the last one. This is the beginning of the last interval. That's the time of the beginning. Plug it into f to get the velocity at that beginning time. Notice this can be converted into the sigma notation we introduced earlier, because every term follows a pattern in our sum. Every term is f evaluated at t with some subscript times delta t, so that's here. And then we've chosen the beginning value for I to be 1. Notice when you plug in 1 here for I, the subscript would be 0. And that's correct because our first term has t0. And then on the second term, I would go up to 2. When you plug 2 in here, the subscript will be 1. So you get the t1. And then we go to the last value for I, which is n. And notice when you plug n right here, we get t sub n minus 1. And that corresponds to the last term. So you can check to see that the sigma notation actually does give you the correct expression. Now we discussed earlier that this version, right, we use the beginning of each time interval to determine the velocity we were going to use as our constant. We discussed that you could have also used the ending velocity over each subinterval. So the first subinterval goes from t0 to t1. Up here we took the beginning time, t0. In this option we use the ending time, t1. Plug that into the velocity function, you get some constant, and we assume the velocity stays at that constant over the time interval. So we take our constant velocity times the length of the time interval, go to the second interval, do the same thing but use the right endpoint, all the way down to the last time interval. Up here we use the left endpoint of the last interval, and here we're using the right endpoint. This can also be converted to sigma notation. So notice the difference between the two. Here we use t sub I minus 1, that's the left endpoint of each time interval, whereas here t sub I is the right endpoint. And you can check that, right? The first I value is 1, so this would be t1 in our first term. Going up to the last one, when I is n, this will be tn, that corresponds correctly to the last term. Okay, so the next observation we already made was that if we the more often we measure the velocity, the more accurate our estimates will be. So ideally we would measure the velocity every possible instant. There'd be an infinite number of measurements taken. So we take the limit as n, which is the number of measurements, as n goes to infinity. So we take either one of these estimates for the total distance traveled. Those are both here. But then we put a limit in front of it. And once we take the limit of that as the number of velocity measurements goes to infinity, it's no longer an estimate. It is now the exact distance. So the limit is what takes us from just having an approximation to now knowing the exact distance traveled over the entire time interval. And what we really want to take from this example is this expression here, these two expressions, are exactly the same that we found, same as the formula we found for the area below the curve. And you can see the function used is f, so it's the area below f of t over the time interval that the subdivisions spanned, which here we just called a to b. So the suspicion we made earlier based on our intuition that the area below the velocity curve gives us total distance, these calculations confirm it because we were able to relate it back to the formula we derived earlier for area below a curve. In section 5.1, we just learned the area problem and the distance problem, and we developed a strategy to solve those problems. But our chapter is called integrals, and we haven't even used that word yet. So in section 5.2, we're going to define something called the definite integral. And this is a name given to an operation that corresponds to the strategy we just made for solving the area and distance problems. So in this section, we'll give the definition of the definite integral, and we'll learn some of properties and how to work a little bit with integrals. Here we see the expression we derived in the last section to solve the area problem. So the area below this curve f over a given x interval. And the same expression appeared when we solved the distance problem, right? If f represents a velocity function and we wanted to find the total distance traveled over a time interval. So it turns out this expression occurs in many situations. It's not limited to those two. And because of that, we want to give it a special name because it's used very often. So on our next slide, we're going to define the definite integral to have this formula. So we'll introduce the notation and all the details of the definition. Here's our formal definition of the definite integral. Now there's a huge amount of writing here. Before we get into the details, let's just jump down to the main part of the definition. This is the expression we just reviewed on the previous slide that we derived earlier to find the area below the curve f over a given x interval. Now here's the notation for the definite integral. So this symbol here, it's like an elongated S. That's the integral sign. And to the right, we put the function that we're integrating. And in terms of the area problem, that's the curve that defines the top of your region. We're finding the area below the curve f. Now, the a to b, that represents the original x interval, right? If you're finding the area below a curve, it was always over some x interval a to b. Right? And suppose the curve f is here. So this is the area we're calculating. So the a and b are placed on the lower and upper parts of the integral sign. The dx comes from here, right? In our calculations, we had this term delta x, which is the width of each subinterval. In the integral notation, we convert the delta to the letter d, so it's dx. Okay, so that's the main point. We're defining this definite integral using this notation to have the formula we derived earlier for the area below the curve. Now let's go through all the details. Now all of this should be familiar because we discussed most of these, I think all of these ideas in the last section when we developed this formula here. So f is our function. We're looking on an x interval from a to b. We divide that into n subintervals of equal width. We saw this formula earlier. For the width of each subinterval, you take the total length of the subinterval, right endpoint minus left endpoint, divided into n equal pieces. Then we give names to all the subdivisions. So x naught is the starting x value, which is the same as a. And then you add delta x to get to the next one. We call that one x1. You add another delta x, get to your next one, call it x2. You keep adding delta x's till you get to the right endpoint b, and that one would be called xn. Then we take our sample points, right? We discussed the idea of sample points before. Within each subinterval, you choose any point in that subinterval and you call it a name like this. So in the first subinterval, wherever you choose your point, your sample point, you call it x1 star. And in the second subinterval, choose your sample point, call it x2 star, all the way down to the last one. Okay, so then we define the definite integral of f from a to b to be this formula we just discussed. Now because it involves a limit, we know limits sometimes exist and sometimes they don't. So this definition only applies if the limit exists and if the choice of the sample points makes no difference. So you always get this, the limit always turns out the same no matter how you choose your sample points. So if this limit does exist, here's our new term we're introducing. We say that the function f is integrable on that interval from a to b. And just a note about this integral sign. So as I mentioned, it's an elongated s, and the reason why it comes from the letter s is because the integral is a limit of sums, right? The sigma notation means we have from I going 1 to n means this is a sum of n different terms. And then we're taking a limit of that sum. So when you see the integral sign, it's like a sum, but it's actually a limit of a sum, as the number of terms in that sum, n, goes to infinity. Now I want to introduce some terminology associated with the definite integral. So this is the notation we learned for the definite integral of a function f over an interval ab. The function inside here is called the integrand, and then these numbers a and b are called the limits of integration, and they come from that x interval that we started with. A is called the lower limit, b the upper limit. Now the symbol dx, as you remember, that came from the delta x when we were doing the sums of the areas of the rectangles. In the integral sign, we converted the delta x to a dx. So by itself, dx doesn't mean anything at this point. It always is paired with the integral sign. So you have the integral sign on the left, the dx on the right, they always go together, and then the function that you're integrating in between. So this is all just one symbol. We can't separate the pieces. So also, the x can change to match any letter name you choose for your independent variable. So this tells us when you see dx, it tells you the independent variable is x. So as I was saying, you could change to a different letter. So here we've changed to having t as our independent variable, so we use dt instead of dx. And in that case, you have to also reflect that in your function, f of t. In the parentheses, that t tells you that the independent variable is t. And here we've switched it to another letter, r, right? As long as you switch it in both places, they always have to match. So all three of these things represent the exact same situation. If you actually had a formula for your function f and numbers for a and b, this definite integral would produce a number that represents the area below the curve. And all three of these would give you the same number, right? These all mean the same thing. We saw in the definition of the definite integral, we had this expression using the sigma notation. So this again is the sum of terms that look like this. And then in front of that we had a limit as n goes to infinity. So if you remove the limit and you just look at the sum, so this is a finite sum of n terms added together. This particular type of sum is called a Riemann sum, and it's named after a mathematician back from the 1800s. And so we interpret the Riemann sum as the sum of the areas of the rectangles in a picture like this. And we also interpret that as an approximation to the area below the curve. So that's how we want to think about Riemann sums. Also, our argument so far has been, for this area problem, has been based on our function being positive. We haven't dealt with the case where the function dips down into the negative y values and how that would affect our interpretation of areas of the curve. So we know as long as the function's positive, the Riemann sum is interpreted as the sum of the areas of these approximating rectangles. And we'll discuss the case where we have a negative function soon. As we've been discussing, we now have our graphical interpretation of this definite integral that I've written here. We now interpret that as the area below the function f over the x-interval a to b, as in this picture. So here's our function f, our interval a to b. The blue region is the region we're considering below the curve, and the definite integral tells us that area. Now we want to extend to the situation where our curve has at least some negative values. So notice our blue curve here has some negative y values. So think about what happens when we make our approximating rectangles. The part that corresponds to the positive part of the curve is the same, right? You pick your sample point, you calculate f of x for the height, multiply it by the width. Now over here, when we follow our formula, we pick our sample point, you find the f of x will be negative. So we're still going to use the same formula, right? To find the area, it would be f evaluated at the chosen sample point times delta x, but this f of xi star will be negative. And delta x is always the same, it's always positive. So when using our formula in our Riemann sum, these rectangles here will all be calculated as negative values. And then we add up the areas of all of them, although these areas are negative numbers. So they still represent the area, they just have a minus sign in front of them. So what that tells us is how to interpret the definite integral in a case like this. It will add up the areas of the rectangles, but the blue rectangles will be counted positively in the sum, and the goldish rectangles will be counted as negative areas in the sum. And so when you add them all up, we get what we call the net area. I just used the term net area, so here we'll formally introduce that term. So we now interpret a definite integral as a net area, which is a difference of areas. So here's our definite integral notation, and we can interpret it as some positive area minus another area, and those come from here. The area below the curve always goes from the curve to the x-axis. So even when the curve is negative, this time we have to move upward to get to the x-axis. And so the area that's counted as positive are these blue regions, and then this gold region is counted negatively. And that's all summarized over here. So the net area is the blue areas minus the gold area. In this example, we're given a function and an x-interval and asked to evaluate the Riemann sum using 4 subintervals and taking our sample points to be the left endpoints. So I want to start by making a number line showing our x-interval from 0 to 2. And let's show where the subintervals are going to be. So we want to divide that into 4 equal pieces. So we'll cut it in half, and then cut that in half, and then there's another one here. Now it's pretty clear here where those marks are going to be, but as I mentioned before, if it's ever not clear, we use our delta x formula. So the formula again is b minus a divided by n. So here a is 0, b is 2, so we get 2 minus 0 over the number of subintervals, which is 4. And this simplifies to 2 over 4, which is 1/2, or 0.5 if you want to use decimals. So that tells us we're going to step 0.5 units to get from one endpoint to the other. And notice that means there will be 4 of those, right? So we go from 0 to 0.5. The next one will be 1, and then adding 0.5 we get 1.5, and then finally to 2. And so if you were using our standard notation, we would start with x0, x1, all the way to the end as the names of those locations on the x-axis. Okay, so then let's think about our Riemann sum. Since we're using left endpoints, our notation would be L sub, and there are 4 subintervals, which means 4 rectangles, so it's L4. And then for our first subinterval, which goes from 0 to 0.5, we would take the left endpoint of 0 and plug that into the function. So we'd have f of 0 times delta x, and then plus, we go to our second subinterval, which goes from 0.5 to 1, take the left endpoint, which is 0.5, plug it into the function. So f of 0.5 times delta x, plus, go to the next subinterval, 1 to 1.5, choose the left endpoint, which is 1, so we have f of 1 delta x. And then for the last subinterval, it goes from 1.5 to 2, choose the left endpoint. We've got f of 1.5 times delta x. Now let's do some calculations. So f of 0, look at the formula for f up at the top. So it will be 0 minus 2, so that's minus 2. The delta x we just found is 1/2. I'll go back to fraction form. Plus, now f of 0.5 will be 0.5 squared minus 2. Right, so 0.5 squared is 0.25, and then when you subtract 2, you get minus 1.75. Okay, so then we'll make this minus 1.75 times our delta x, which is 1/2. I'm kind of mixing decimals and fractions here, but that's okay. Then we go to f of 1. So that's 1 minus 2, right, which is negative 1, times delta x is 1/2. Okay, now f of 1.5. So 1.5 squared is 2.25, and then when you subtract 2, we get 0.25. And then the delta x is 1/2. So then when we simplify, this first term will be negative 1. The next one becomes minus 0.875. And then the third term, minus 1 times 1/2, is minus 0.5. And then the last term, 0.25 times 1/2, is plus 0.125. And then all this together comes to negative 2.25. So that's our answer. That's our Riemann sum we were asked to find. Now let's relate this to the graph. So here's a quick sketch of this function on the x interval from 0 to 2. So if we plotted a few points in the function f of x, when x is 0, y is negative 2. When x is 1, y is negative 1. When x is 2, y is going to be 4 minus 2, which is positive 2. Right, so this is a parabola that's been shifted down 2 units, just part of it. So the area we're looking for is this region, and then this this region. Okay. And as we know, the region that is above the axis will count positively, and the region below will count negatively. And of course, we approximated this using rectangles. So if we just put kind of a rough sketch of the rectangles we used, the first one went from 0 to 0.5. We used the left endpoint to determine the height. On the next one, the left endpoint is here, determines the height. Left endpoint. And then this one, left endpoint. And if you look at the signs of our terms, the first three terms were negative. That corresponded to these three rectangles. The fourth one was positive. That's this rectangle here, right? It's shorter than the actual shaded area we were wanting to find, right? And so overall, the negatives outweighed the positives, right? This one had more of the graph below the axis with the negative y values compared to above. So we don't really interpret this now as the area below the curve because of how we counted these negatively. Right, we call that the net area, but this is only an approximation to the net area because we didn't use a limit, right? We only added up 4 terms of these approximating rectangles. As we developed our strategy for finding the area below a curve, we always defined, when we created our subintervals, we always created them with equal width, and we continued using that in our calculations for this definite integral. I just wanted to mention that keeping them equal width is not a requirement. You could use subintervals of unequal width, and there are some situations where that might be useful. So in that case, the delta x could be different for each subinterval. So we notate them delta x1, delta x2, etc. But they all have to become smaller in width as you take the limit. So the requirement is that all of these delta x's have to approach 0 as you keep increasing in the number of subintervals. So a simple way to guarantee that they're all going to 0 is to take the limit as the maximum of the delta x's approaches 0. So in that case, the limit looks like this. Everything's the same here as in the previous definition, but instead of having n go to infinity, we express the maximum of the delta x's must go to 0. We introduced the term integrable earlier, and so that refers to a situation where the definite integral of a function exists, right? We said because it's defined as a limit, it won't always exist. So we have a theorem here that gives us some conditions that guarantee that a definite integral will exist. And those conditions are if your function is continuous on the closed interval that you're considering, or f doesn't have to be continuous, but if it has only a finite number of jump discontinuities. In either of these situations, the function would be integrable over that x interval. In other words, this definite integral will exist. We're not going to give a proof of this, but let's just think about it and see if it makes sense. I'm going to sketch a graph of a function that's continuous over this interval from a to b. Right? So in terms of the definite integral, it represents the area below that curve. And that seems like a clearly defined area. It's going to be finite for sure, and you can easily see how the rectangle method would work. The rectangles would fit in there nicely, and we could approximate the area, and it just clearly seems that area would exist. Let's sketch another one where the second condition is met. So f is not necessarily continuous, but it could have a finite number of jumps. So it might start out continuous, and then right here it jumps, then there's a little continuous piece, and then right here it jumps again, and then it finishes. So is there a clear area below the curve on this case? Right, so if we cut it off at the endpoints, it does seem like if you shade below this curve, put it in yellow, if you kind of put a vertical line where it has the jumps and just keep that as your boundary, right, it does seem like there's a clear area in that case also. So now let's go to a case where the hypotheses of the theorem are not met, where the function has, say, an infinite discontinuity. That would be one situation where that condition is not met. So we could have a vertical asymptote, for example. So there's our function. Let me put it in purple. So what would be the area below the curve here? Right, there's definitely the potential that area could be infinite, because notice how it goes up infinitely high right here. So in a situation like this, it's possible that the definite integral of f may not exist. And notice this case, where having an infinite discontinuity is not a condition that guarantees the function to be integrable. But because we've just seen that any function that is either continuous or has a finite number of jumps, that tells us that many of the functions that we work with are integrable, because many of the functions are continuous, right? Polynomials, exponential, logarithmic, some of the trig functions, sine and cosine. Now, there are several functions we work with that have vertical asymptotes, like rational functions and some of the trig functions. So it's possible those are not integrable over certain intervals. I wanted to talk a little bit more about the notation for the definite integral. So the notation was developed by Leibniz, right? The same guy that made the Leibniz notation for the derivative that we learned. And so he chose these symbols. So notice this is the definition of the definite integral written in its limit definition form. And we discussed before that the integral symbol is replacing the limit and the sigma. So it represents a limit of a sum. And then notice here the sample point xi star in the integral notation just becomes plain x. And we've discussed before how the delta x becomes dx. So keeping that in mind, let's look at this simple example. So here we're given this expression, and notice it's a limit of a sum, and it ends in a delta x. In calculus, you want to get used to recognizing that type of expression as fitting the definition of a definite integral. So we need to realize that this part is the f evaluated at, in this case, xi, right? We see instead of x's there, we see xi's. And so to write this in the integral notation, we replace the limit and the sigma with our integral sign. Now we'll have to put the endpoints on, the limits of integration. Those do not appear in this expression. You have to know with some outside information what the x interval was that got divided up by these x1, x2, x3, and so on. So here that was given. The interval is 0 to pi. So the left endpoint 0 goes on the bottom, the right endpoint pi goes on the top. Now here we're going to take this expression, this is like the f of xi star, but here we just called it xi, and we want to just replace all the sample points notation with just a plain x. So these xi's will be changed to x. So we have x cubed plus x sine x. And then the last piece, this delta x at the end, in the integral notation gets replaced with dx. Here we're asked to evaluate this definite integral in two different ways. First, using areas, and second, using the limit definition of the definite integral. So let's start with the area method. So what we need to do is sketch the function. Now you can find the function because it's in between the integral sign and the dx. So here we can see f of x equals 2, a very simple function. So in part A, we want to graph that function, which of course is just a horizontal line at height 2 on the y-axis. So here is this line. This is our f of x. Now look at the limits of integration from 1 to 3. So on the x-axis, we need to mark off those values. So we're starting here at 1, ending at 3. Those are going to define the sides. And the area we're looking for is right here. And notice it just happens to be a rectangle, which we can easily find the exact area of. We don't have to do any approximations with subintervals or anything like that. So here the area is just the product of the two dimensions. So notice it's 2 in this direction and 2 in the other direction also. So it's 2 by 2. And we get 4. So we can say this definite integral, just copying it from the problem, equals 4. So this was an unusual case in that we could easily find, interpreting the integral as an area, we could easily find that area, and that's because the top was a straight line. That made this just turned out to be a rectangle, so it's very easy. Right? In many cases the function is curved, which makes calculating the area using familiar formulas impossible. So let's go to part B. So here I'm going to copy the integral. Okay, and then we want to use the limit definition. Okay, so if you remember the definition, it's limit as n goes to infinity of the sum of the, and it's going to be the sum of n terms, so our index will go from 1 to n. And then the definition says f evaluated at your sample point, xi star, times delta x. Okay, that's just the straight definition. We haven't even substituted in anything yet. So let's think about where the sample points are going to be and what the formula is for delta x. Let's start with the delta x formula. Right, so we know it's a fraction. In the numerator, we take the right endpoint minus the left endpoint. So here that would be 3 minus 1 over n. Now we don't know the number of rectangles, and in fact that's not fixed because we're going to be taking the limit as n goes to infinity. So we need to keep it here in terms of n. And so it simplifies to 2 over n. Now let's think about the sample points. We can, remember, you can choose them to be anywhere within the given subinterval. So we're going to choose the sample points to be the right endpoint. That'll probably simplify our calculations. So notation-wise, the ith subinterval goes from x sub I minus 1 on the left up to xi on the right. So the xi star will be the right endpoint, which is just xi. Okay, so now that we have those two pieces, we can substitute into our formula here and we'll do that part starting on the next slide. So let's look at the sample points in more detail. So remember, our interval goes from 1 to 3. So the x0, the first endpoint of an interval, would be at 1. Now we take a step delta x units. And remember, delta x we just found is 2 over n. So the next point will be, notice we were at 1 here, and then we moved a distance 2 over n to the right, so this point would be 1 plus 2 over n. And that's what we would call x1. Then we make another step of 2 over n to get to our next subdivision. So this would be 1, let me show it here, this is where we left off, and we add 2 over n to that. So that would be 1 plus 4 over n. Right? And then we add another step of 2 over n. So here's where we left off. When we add 2 over n to that, it becomes 1 plus 6 over n. And then you keep doing this till you get to the end. And so if we name these in the usual way, x0, x1, and so on, we want to see if we can generalize a formula for xi. Okay, so notice they all look like 1 plus some number over n. Now let's see if we can figure out what the numerator is there. So if the subscript is 1, the numerator is 2. If the subscript is 2, numerator is 4. Subscript 3, numerator is 6. Notice the numerator is always double the subscript. So if the subscript is I, the numerator would be 2i. So that tells us the locations of the subdivisions. Now let's look at the sample points. So remember, we chose the sample point on the last slide. We chose xi star just to be the right endpoint, which we determined is xi, which is now this formula. Okay, so now we have more of the pieces we need. So last time we had written this, right? This is the integral we're dealing with. We just first wrote the plain limit definition of the definite integral, nothing specific to the problem yet. Now we can start substituting in. So we're not ready to take the limit, so keep the limit sign. Keep the sum sign. Now here, f of xi star. We just found xi star right above. It's 1 plus 2i over n. And then the delta x we found on the previous slide was 2 over n. Now here's where we can use the formula for the function to evaluate this. Remember, our function here was very simple. It was just f of x equals 2. So it actually doesn't matter what you plug into f, this will always just equal 2. So that's really going to simplify things. So in our next step, we keep our limit sign, we keep our sum, then we have 2 times 2 over n. And then the next obvious simplification is to do the 2 times 2, which is 4. So let's keep our limit sign and our sigma. And then we have 4 over n. Now let's look at the sum part. So let's keep the limit sign. Now the sum says I goes from 1 to n. So what you do is you plug I equals 1 into here, and then you do plus, and then you plug I equals 2 into here, plus, plug in I equals 3 until you get to the end. But notice there's no I in here at all. So here's what it looks like. When we plug in I equals 1, we get 4 over n. Then we do a plus. We plug in I equals 2, which is also 4 over n. Plus, continue all the way till you get to the last one, which we plug in n for I, but again, there's no I to plug in for. They all look the same. So the important observation is there are n terms here added together. Right, once for each index. This was when I is 1, this is when I is 2, all the way down till when I is n. So there are n of these. So if you add a number to itself n times, it just means take that number and multiply it by n. So now we keep our limit sign. What we decided is we have 4 over n added to itself n times means multiply by n. Notice the n's cancel. So we're left with just 4. Now we can use our limit taking skills from earlier. This is a very simple limit, right? Limit of a constant is just that constant. This is the same answer we got for part A, right? So we still, in both methods, we concluded the value of this definite integral, which I need to correct here. The function we integrated was just 2 equals 4. Now in part B, it was a huge amount more work than part A. Right? Calculating the area was very simple, but in most cases, part A, that area method isn't going to work. Now this function I chose for this integral was incredibly simple, right? F of x equals 2. The more complicated f gets, the harder this process is. And I'm not going to expect you to do many problems like this at all, because I just want you mainly to see how difficult this can be to use the limit definition of the definite integral, especially this part here, trying to figure out what this sum will be. This time it turned out very simple, but making the function any different from a constant, this can get a lot more challenging. We had the same issue with derivatives, right? When we first defined the derivative, it was a limit definition, and we did a few problems where we actually calculated a derivative using that limit definition. And it was a lot of work, and we saw that in many cases it would be pretty much impossible to do by hand. So we spent a long time learning shortcut methods, various rules and formulas, so we could calculate derivatives without having to use the limit definition. So we're going to need to develop the same ideas here for the integral, because using this limit definition is very difficult. So we're going to leave most of that to Calculus 2. You'll be learning a large number of techniques to help you evaluate various definite integrals where you can avoid having to use this limit definition, but you'll still get to the same answer. Now we're going to spend some time learning some of the properties of the definite integral. So the first property we're going to look at has to do with changing the order of integration. So in the limits of integration. So when we first defined this integral, when I made a sketch to go along with it, we said the x interval was from a to b, and we always assumed a was to the left of b. In other words, a is less than b. That's the standard way we think about an interval. But you could apply the limit definition using our Riemann sums for this case, even if a is greater than b. Right? So we could reverse the order. So if we do choose to reverse the order, your delta x in the formula would change. Right? The delta x is always the top number minus the bottom number, which when it's written in this form, it would be b minus a over n. If we change the order and put b at the bottom, a at the top, when we find delta x, we would use, again, the top value minus the bottom value. It would become a minus b. Everything else would be the same in the limit definition of the definite integral. So notice that the second version of delta x is just the negative of the first version. And so all it does is introduce a negative sign into the delta x term. So the result is, if you change the order, and so you put, the standard is to have a at the bottom, b at the top. If you switch those, put b at the bottom, a at the top, you'll get the negative of the value of the original definite integral. Okay, so just a quick example. We found in an earlier example that the integral from 1 to 3 of the function 2 dx is equal to 4. So now we know that if we change the order of integration and went from 3 to 1 of the same function, we would get negative 4. And you could go through the whole limit definition of this integral and calculate it the long way like we did for this one. And if you did all that work, you would get negative 4. Okay, but if you've already done this one, no need to redo it. You just know you're going to get the same number but the opposite sign. The next property is up here, and this has to do with if your limits of integration a and b are actually the same, what would be the integral? Well, in this case, the x interval has no width, right? So the delta x, right, if you think of the delta x formula, it's b minus a over n, but if b and a are equal, then the numerator is 0, so 0 over n is 0. So the delta x is 0, so the width of each sub-rectangle is 0, and so the area is going to be 0. Right, so we have this property. The integral here will turn out to be 0 if you're integrating from one number to the same number. Now here's a list of 4 properties that we're going to go through next. For these properties, we will assume f and g are continuous because that guarantees they're integrable. So let's just read through them quickly. The integral of a constant from a to b is equal to c times b minus a. The integral of a sum equals integral of the first plus integral of the second. Integral of a constant times a function is the same as if you pull the constant out in front and then multiply it by the integral of f. And then 4 is similar to 2, it's just a difference instead of a sum. Okay, so we're going to go through these properties one at a time and give an argument for why they're true. So this is property 1 that we just saw, the integral of a constant function. And we're claiming this is how you could calculate the value of this definite integral. So one way, before we give the argument, one way to interpret this statement here is that the integral of a constant is just equal to that same constant multiplied by the length of the x interval. Right? The x interval here is from a to b. Now here's the argument. The function we're integrating is inside between the integral and the dx, so the function is f of x equals c. So y equals a constant is a horizontal line, so that's sketched here in this blue line at height c on the y-axis. We've marked off our x interval from a to b, and we know that the definite integral represents the area below the curve over that interval, so this shaded blue area. This happens to be a rectangle, so we can easily find the area. The height is c, and the length here is just right endpoint minus left endpoint, so b minus a. So the area is the product of the height times the width. And that gives us this formula here. This is the second property. It says the integral of f plus g equals the integral of f plus the integral of g. So in other words, you can split up the integral over a sum. Or another way of phrasing this, the integral of a sum equals the sum of the integrals. Now this is not too surprising because we saw the same thing with derivatives, right? The derivative of a sum, you could split the derivative up to each individual term. Okay, so same thing with an integral. Now let's think about graphically what this is telling us. Suppose you have two functions f and g. You can create the function f plus g by adding vertical lines. So for example, at this x-coordinate, you would take the corresponding y for f, and you take the corresponding y for the function g, add those two together, and it would take you up here in this case. And you do that for every single x value, right? You add the f of x value and the g of x value. That gives you the y value for the f plus g function. Now, the integral of f plus g is the area below this curve, which is this entire region here. Now let's look at these two. So the integral of f is just the area below the curve f. The integral of g is the area below g, all the way down to the x-axis. When you add those two areas, right, so this area with the blue vertical lines, and this area, which is shaded blue all the way down, that's going to give you the area below this very top curve of f plus g. That's the graphical interpretation of this property. But we'll use this property a lot. So again, the idea, the integral of a sum, you can just split the integral up to each individual term in the sum. Property 3 says that if you're integrating a constant times a function, you can pull that constant out in front of the integral sign. And you can give a similar graphical argument that we did for the property for the integral of a sum, so we're not going to go through that one now. Property 4, integral of f minus g. Same thing, you can split the integral up to each term, but just keep the minus sign. So this can be proved using properties 2 and 3 by rewriting f minus g as a sum, f plus negative g, and then view the negative g as negative 1 times g, so it's a constant negative 1 times the function g. You can use this property to pull the constant, the minus 1, out in front. Now we're going to see how we can use some of the properties we've learned in this example. So we're asked to evaluate this integral, and notice there's a difference. So one of the properties we saw, first let me just copy the problem, said that if you're integrating a difference, you can split the integral up to each term individually. So we first integrate 3, and then you put its own dx for that integral, and then the minus sign, and then we integrate the second term, the 5x, and that integral also has its own dx, because we always pair an integral sign with the dx with the function inside. Same thing here, integral dx, function inside. Now the first integral here is the integral of a constant, and we had a property about that. We called it property 1. So it said the integral of a constant is just that same constant multiplied by the length of the x interval. Here we're integrating from 2 to 4, so to find the length you take the top value minus the bottom value, so that would be 4 minus 2. Then we have a minus sign. Now the next integral, we have a constant times a function. So we learned a property that said you can pull the constant out in front of the integral sign. And notice every time I write the integral sign, I use the same limits of integration as the original, 2 to 4. Now there's only one integral left, and that's this integral of x over the interval 2 to 4. We don't automatically know what that is from our properties, so we're going to use, we could use the limit definition, but we know that's going to be a lot of work. So let's see if we can use an area argument to find that one. So let's go off on the side and do some work on just this integral from 2 to 4 of x dx. So the function we're integrating is f of x equals x. So let's start by sketching that function. And that's a very simple function to sketch. It's a straight line, of course. Just marking off some points on my axes. So y equals x passes through the point 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, right? And then the interval we're considering is from 2 to 4. So this is the area we're trying to find. Let me highlight it. So it's not a rectangle, so it's not going to be a one-step calculation, but we could break this into two pieces by putting a line right here. The bottom part is a rectangle and the top part a triangle. We can find both of those areas. So that rectangle at the bottom, notice its dimensions. Let me point out here. So obviously that part's 2. Now this part, notice this is x-coordinate 2, and so this is the point 2, 2. Right, so that tells us that height is 2. So that's a 2 by 2 right there. So the area there would be 4, of course. And then for this top triangle, right, so the area of a triangle is 1/2 base times height. The base is the same as the rectangle, it's 2. And then the height, let's see if we can find that. This is the point 2, 2, so it's at height 2 on the y-axis. This is the point 4, 4, so it's at height 4. So the distance between 2 and 4 is just 2. So the height of that triangle is 2. And so that product of those three numbers simplifies to 2. So that's the area of that triangle. So that tells us the definite integral that we're considering here would be the sum of those two areas, 4 plus 2, which is 6. So now we can come back up here, and we know that this integral comes out to be 6. So let's do our next simplification. We get 3 times 2 minus 5 times 6. We get 6 minus 30, which is negative 24. Okay, so we just evaluated this integral in part by using the properties that we just learned, and then there was one integral left after we used our properties, and we just made an area argument to complete that. This is another property of an integral, and the idea is we have an original interval on the x-axis from a to b, and then we divide it somewhere in between at a point we call c, and that creates two subintervals. So this property says if you consider the original integral over the entire interval from a to b, right, that would be interpreted as the area below this curve over this entire interval, That's the same thing as breaking it up into two integrals and adding them together. The first integral goes from a to c and the second from c to b, which you can see down here. So the first integral goes over this part. The second integral goes over the second subinterval. And so in terms of areas, on the left we have the area below f from a to c, so that's this darker blue area, plus the area from C to B, which is this very light colored area. And clearly, when you add those two areas up, you get the area under F over the bigger interval from A to B, which is represented here. So the graphical interpretation of this makes it very clear why this property is true. Here we're given two integral values. First, we're told the integral of f from 0 to 4 equals 12, and also the integral of the same f from 0 to 7 equals 18. And we're asked to find the integral of that same f over the interval 4 to 7. So notice all these different limits of integration, but they use some common numbers, right? 0, 4, and 7 appear multiple times. So that makes us think of this property we just learned. So if we sketched an x interval, the important numbers we saw were 0, 4, and 7. So the property says if you integrate over the biggest interval, which would be 0 to 7, and then of our function f, that's the same as breaking it up and first integrating from 0 to 4, and then add to that the integral from the second subinterval, which is 4 to 7. Now notice they gave us the values of two of those. Right? They told us the integral from 0 to 4 is equal to 12. And they also told us the integral from 0 to 7 is 18. So if we make those substitutions, we now have 18 equals 12 plus this other integral that they didn't give us, but notice that's the integral they asked us to find. And so now just subtract 12 from both sides. We get 6 equals this integral. And now we know the integral they asked us to find has a value of 6. To summarize what we talked about today, we started with section 5.1. In the previous lecture, we had discussed the area problem, and today we discussed the distance problem. And this problem is if you know the velocity, and especially if the velocity is not constant, how can we use that information to find the total distance traveled? And one of the main conclusions we found from that was that if you graph the velocity function, the area below the velocity function over your given time interval, that area represents the total distance traveled. Then we started section 5.2 on the definite integral. First, we defined the definite integral, and the definition basically came from the formula we had developed earlier to solve the area problem, right? The area below a function f over a given x interval. We saw that this definite integral was written as a limit of Riemann sums. Okay, so we defined a Riemann sum, and graphically it represents the sum of approximating rectangles. And then when we take the limit of that as the number of rectangles goes to infinity, that is our definition of the definite integral, which represents the area below the curve. We also discussed the term net area. So the definite integral actually finds net area, which means it counts regions that are below the x-axis as negative towards the calculation. And then we finished by learning some of the properties of integrals. We still have more properties to go, so we'll do those starting in the next lecture.